After understand the idea of deep learning and why we should use deep structure to construct the neural network, now we are ready to really construct a deep learning structure, construct a deep neural network to do practical things. So in the following materials, we will introduce several tips to train the deep neural network. So in the construction of deep neural network, we have 3 steps. The first step is to define a set of functions, or we said that we have to define the network structure. And then we define how to measure the goodness of function. And then we will use the gradient descent algorithm to pick the best function, so that we can, and by giving a set of training data and the ground truth, we can construct a neural network. Okay, so when we finish the training, we need to examine whether the constructed neural network is good or not. Okay, and basically when we try to tune our network, neural network, we need to consider two situations. The first one is, do we have already good result on training data? That means when we train this neural network, if we put training data into this neural network, can this neural network can do very well for the training data? If not, that means we haven't select the best function right now. We haven't had the good network structure. So we may need to redesign the structure. We may need to change the parameter we train the neural network. Okay, so if we don't achieve high training accuracy, the so-called training accuracy is that we put the training data into the neural network and then to see the accuracy of the classification, for example. Okay, so if we don't achieve good training accuracy, we need to change the parameter to train the neural network. Okay, if we already have good result on training data, then we then have to check if we have good result on testing data. If not, that means we have good result on training data, but have bad result on testing data. That is the so-called overfitting. Okay, overfitting is a terminology in machine learning. That means our constructed model put too much emphasis on the characteristic of training data, and the model can describe the training data very well. However, it cannot be adapted to testing data, where the testing data may have different, slightly different distribution features, or there are more variation on the testing data. So if we achieve good training accuracy but bad testing accuracy, that is called overfitting. Then we still have to do a parameter change. Okay, and the strategy to change the parameter is different from tuning our model to get good training data, good training accuracy. Okay, and if we also achieve high testing accuracy, then our task is done. Okay, we already have good result. So in the following, we will introduce several tips to construct a better neural network. And this is the reason why we don't always blame overfitting. In conventional machine learning technology like SVM, when we achieve bad testing accuracy, we may blame that, okay, this model is overfitting. However, in neural network, the problem is not always due to overfitting. That may be only because of you don't very well train your model. So we can see two figures here based on training data. And if we construct a model consisting of 20 layers and another model consisting of 56 layers, okay, and we see that as the iteration increase, numbers of iteration increase, the training error decrease. However, the deeper network has higher training error, okay, and the relative shallow network has lower training error. So if you see this result, you will say that the deep learning does not work. If you use more layers, the training error increase. So deep neural network does not work. Okay. However, if you also try testing data on these two models, we also see that the testing error of the deeper network is higher. Okay, so actually this problem is not due to overfitting. This is the problem that you don't really well train your model. And this situation is different from conventional machine learning model like SVM, because in support vector machine, when you construct a model, that means you already solve the mathematical equation that is defined to do a support vector machine. Okay, so nothing else you can do to improve such SVM. However, in deep learning, we can improve this model by adjusting different parameters. So we need to consider two different situations. If we want to increase the training accuracy, we have some strategy. If we want to increase testing accuracy, or we want to reduce the problem of overfitting, we have different strategy. So different approach may be used for different situations. And in the following, we will first introduce several tips to increase training accuracy. Okay, the first one is choosing proper loss. The second one is mini-batch, and the new activation function, adaptive learning rate, and momentum. The first tip is to choose proper loss. Remember that when we train a neural network, at the final stage, we need to choose a loss function to represent the predict result and the ground truth. So we need to measure the loss between the predicted result and the ground truth. Okay, and actually we have several ways to measure the loss. The simplest way is called the square error. That means we just take the difference between the predicted result and the ground truth and sum them together to get the total square error. And there's another commonly used loss function that is called cross entropy. Okay, cross entropy comes from information theory. That is a technology commonly used to measure the difference between distribution of two random variables. Okay, so we can view the predict value as a random variable and the ground truth as another random variable. And this is the formulation to measure the cross entropy between these two random variables. Okay, so we can either choose square error or cross entropy to be the loss function. That would be quite easy. So originally, if you use square error to measure the goodness, but you achieve bad training accuracy, maybe you can try cross entropy to measure the loss. So let's try it. Here is an example. The x-axis is the numbers of EPUB, and we will introduce this item later. That is more likely iteration. Okay, you can think that here. And then the y-axis is the training accuracy. And we can see that if we use the square arrow, then the training accuracy keeps low. And when we use cross entropy, based on a toy example, we can increase the training accuracy largely as we increase the numbers of iteration, numbers of training iteration. So, so this would be the simplest way to try to enhance your training accuracy. And why does this work? Why just changing the loss function will change the performance a lot? Okay, that is from this paper. They show that when we choose different loss function, actually the surface or the distribution of the loss function change a lot. Like if we use the square arrow loss function, the loss function surface maybe look like this red surface. And then when we use cross entropy loss function, the loss surface maybe look like the black surface. And we can see that the highest part and the lowest part of the cross entropy surface is much wider. Okay, so the distance between high loss and the small loss is quite large. Okay, so in this paper they suggest when using softmax output layer, choose cross entropy loss function. So this is the first tip you can do. The second tip is called mini batch. Remember that when we when we calculate the loss function, basically we mean that we put all the training data. We put all the training data into the neural network, and then we predict all the result for the we predict the result of all training data, and then we compare the predicted result with the ground truth. And if, for example, if right now we have 1,000 training data, and we have 1,000 ground truth, okay, so conventionally we put all this 1,000 training data into the neural network, and then get 1,000 predicted result, and then calculate the loss, and then sum all the 1,000 error loss, 1,000 loss together. Okay, so this is the traditional way. But the approach of mini batch means we just take subset of the training data each time. Each time we just take subset of the training data and calculate the total loss of this subset. So for example, in the first mini batch, we just take the first training data, the number 31, number 61, and so on, to put into the neural network and get the predicted result of this subset data, and then calculate the total loss of this subset. Okay, and based on this subset total loss, we adjust the parameter of the neural network. Okay, so this is called one mini batch. And at the second mini batch, we take the second training data, the 16 training data, the 32 training data, and so on. So we have another subset, and we predict another predicted result of another subset, and calculate the total loss of this subset. And then we adjust this neural network, the same neural network, by this subset. Okay, and we keep going uh, we keep going, and we take all the subset of the training data. Okay, so the whole procedure is look like this. Initially, we randomly initialize network parameter. Okay, and then we pick the first batch. Okay, the first batch. The first batch may just contain a subset of the training data, and then we update the parameter once, and then we pick the second batch, and then update the parameter once until all mini batch have been picked. Okay, so for example, when we have 1,000 training data, and if we consider 100 data points per subset, then we have 10 subset. We have 10 mini batch, and for each mini batch, we update the parameter of the neural network once. Okay, and after we finish update all the 10 subset, we say that we finish one epoch. Okay, we finish one epoch, and actually we can repeat the same process again and again. So we can do the second epoch. That means we may randomly divide the 1,000 data points into 10 subset, and then according to this 10 subset to update parameters again. So we can finish the second epoch, and then we can do the third epoch, the fourth epoch, and so on. So the main idea of mini batch is that we do not really minimize the total loss. That sounds a little bit weird. However, many experiments show the mini batch approach achieve better performance. Okay, so in this case, we may just take 100 examples in a mini batch. Okay, and then we may have 20. We may have many mini batch. Okay, and we can do we can update parameter according to this subset, according to this batch, and this is called one epoch. And we can repeat the epoch 20 times. We can do 20 epochs to adaptively adjust the parameter of the neural network. Okay. So here again, the L is different each time when we update parameter. Okay. So basically, we don't necessarily at the first subset we always pick the data number 1 and the data number 31. It's not necessary. So at the second epoch, we can randomly select 100 data point to be the first batch, and we can randomly select another 100 data point to be the second batch, and so on. So the data point belonging to a batch can be changed. Okay, that can be different in different epoch. Although this methodology looks a little bit weird, however, many experiment results show that better performance can be given. Okay, so in the original gradient descent, we will calculate the total loss over all training data. Okay, so theoretically, we can have a very complete loss surface, and we can find the best direction to do the optimization, to update the parameter. So we can update the parameter. Initially, we have parameter here, and then we jump to here, and then we jump to here. Okay, and with mini batch, the update procedure looks a little bit more complicated, looks maybe more unstable. So at the first time, according to the first batch, we may jump from this point to this point, and then according to the second batch, we may jump from this point to this point, and then we jump to this point and jump many times. And in the original gradient descent, it may jump 2 times, maybe just 2 times, but right now we may jump many times. So the result seems unstable. in the experimental result. However, in the original gradient descent, we have to update after seeing all example. Okay, and with mini batch, if there are 20 batches, we can update 20 times in one epoch. Okay, so we have more chance to find a good parameter set when we update more times. Okay, because we know that the loss surface may be quite complex and there are many local minima. And if we update more frequently, and at each update, we just see just a small subset of the data point, we can quickly calculate the loss function and we can quickly update. We can make our network more flexible, more active, more aggressive to change the parameters. Okay, so mini batch usually has better performance. So this is the second approach, second tip to increase your training accuracy. And again, mini batch is also faster because at each time, at each batch, we just see a small subset of the data. We don't necessarily see all the data and sum the loss together. Okay, so usually mini batch is faster and is also has better performance. So this is the result of a toy example. So as the numbers of epoch increase, if we don't use batch, that means we sum total loss and then we update the parameter according to the total loss. Then we can see that the training accuracy keeps the same, almost the same. However, if we use mini batch, we can increase the training accuracy as the numbers of epoch increase. Why? That means when we consider the total loss, we may quickly stuck to the local minima, and we have no chance to jump out of the local minima. However, when we use mini batch, we keep updating. We update many times. Okay, and we have more chance to jump out of a local minima. So this is a good approach. This is a good tip to increase your training accuracy. And you, as I said before, you don't necessarily pick the, for example, at the first epoch, you always pick the data number 1 and the data number 31 to be the first batch, and then take the data number 2 and the data number 16 to be the second to be the second batch. Okay, and at the epoch 2, you don't necessarily pick the same data point into the first batch. You can shuffle. You can change the training data at each at different patch. Okay, and you can do that. And if you use some tool like Keras, this is one of the convenient deep learning toolkit. If you use this toolkit, they do the shuffle. They do shuffle of the training example for different batch automatically. Okay, so this is default of this is the default setting of the Keras. Okay, so you can change the data points in the batch differently at different epochs. Now we go to the third tip. That is the new activation function. In early years, deeper usually does not imply better. As I said before, the idea of neural network was proposed in around 1980s, and beginning from 1990s, many technology based on neural network diminished because researchers found that they cannot train a better neural network to do very accurate classification or regression task. So in early year, actually, some researchers think about if we can increase the numbers of layers to improve the performance. However, as we can see in this figure, if we do handwritten digit classification, when we increase the numbers of the numbers of layers, then the result of the training data will decrease. The training accuracy will decrease as the numbers of layer increase. So in early years, many researchers think about this is not a good model, and we cannot achieve a better result. Deeper neural network is not promising. Okay, in early year. So this is the toy result. Okay, so when we increase the numbers of epoch and the training accuracy of the network consisting of 9 layers, the training accuracy is quite low. Okay, and the network consisting of 3 layers, the training accuracy will increase as the numbers of epoch increase. So this is weird. Okay, this figure seems that we show that deeper neural network does not work. Okay, but why? Why in the beginning of 2010, researchers go back to deeper neural network? So there is one important algorithm that is proposed. Okay, there is one important problem that has been discovered in the end of 1990s. Okay, in the end of year 2000. Okay, that is the so-called vanishing gradient problem. Okay, so if we use sigmoid activation function, that is quite commonly used activation function in early year when we construct the neural network. When we use sigmoid activation function, there is a problem called vanishing gradient. That is at the early layers. Okay, we may find that they have smaller gradient. When we update this network again and again, we will find that at early layers, they have smaller gradient. And then the parameter will be updated very slow. And almost random parameter will be learned for early layers. But for late layers, there are larger gradient, and we can learn very fast. Okay, and it's almost converged at late layer. However, this problem is quite significant because this makes the whole neural network simply based on random. So you can imagine that we input data here, and then we do several processing, and this processing, the parameter of this processing are almost random, and then we have good parameters at late layers. We basically base on random data to do the classification. So this is why we see that when we use 9 layers neural network, we achieve almost random guess performance when we do the hand digit recognition. The hand digit maybe 0 to 9, so there are 10 handwritten digits, and the training accuracy to be 0.1, that is equal to random guess. Okay, so because of the vanishing gradient problem, in early year, when we construct a deep network, we will achieve the training accuracy almost like random. Okay, so why the vanishing gradient problem happens? Okay, that is because the activation function we use. If we use the sigmoid activation function, then this is the curve of the sigmoid function. That means we will map the large input value into almost we will compress the large data difference into a small range. Okay, so this is the characteristic of the sigmoid function. Okay, so even if we have large data difference, we will map them into a small range of difference at the output. Okay, so when we use the activation, the sigmoid activation function, we actually compress or reduce the inference of data difference. So we make this value smaller and smaller. And when we calculate the derivative, that is when we try to update the parameter, the gradient will be smaller and smaller, will become smaller and smaller. And this is the so-called vanishing gradient problem. Okay. And in the beginning of year 2000, some researchers tried to solve this problem. Okay. And in year 2006, people use RBM, restricted Boltzmann machine, to do pre-training to solve the vanishing gradient problem. And right now, researchers use ReLU to solve this problem. So what is ReLU? ReLU is the abbreviation of rectified linear unit. Okay, so right now we modify the activation function like this, and we see the characteristic of this activation function is when the input value is larger than 0, then we will output the same value of the input value as the output. And if the input value is less than 0, then we will output 0. So this is quite simple. This is a simple activation function. Okay, and why do we use ReLU? First, it's fast to compute. It's very simple. And we have biological reason to use ReLU, because in our neuron, when the stimulus, the strength of the stimulus is larger than a threshold, then we will handle this stimulus. We will processing this stimulus. Otherwise, our neuron do nothing. Okay, so there are some biological reasons. And actually, the ReLU function is equal to infinite sigmoid with different bias. Okay, so it's a special case of sigmoid function. And by using ReLU, we can solve the vanishing gradient problem. And this is the most important reason we use it. And why ReLU is promising. So let's see this simple example. So originally we have 2 layers, and for each layer we have 4 nodes. Okay, and assume the input value of this node is larger than 0, and this one is larger than 0. Okay, then we will pass the input value to the next layer. And if the input value is less than 0, then we will output 0 to the next layer. Okay, and the same case in this one. And then this, if the data work like this network is equivalent to this network. That is totally the same as we remove part of the node. Okay, because this node is not workable. Okay, so when we use ReLU, that means we construct a thinner linear network. Okay, and we do not have the input do not have smaller gradient is passed to the next layers. Okay, and by adjusting and based on a different value of the input, we may adaptively. It seems that we adaptively remove part of the node. Okay, we remove part of the node, and at this time we may remove uh, the, some subset of the node, and at the next time we may remove another subset of the node. Okay, so we can view the whole neural network as an example of thinner linear network. Okay, or we can see the whole neural network as a collection of a thinner linear network. Okay, so right now we are not only consider one neural network. Actually, we can view them as a collection of smaller and a simple network. So from this toy example, when we use sigmoid activation function, the training accuracy keeps the same, almost random. And when we use ReLU activation function, we can largely increase the training accuracy. So this is also very simple but important alternative to enhance your training accuracy. You can just replace sigmoid by ReLU. And actually, there are some variations of ReLU function. Some researchers propose liquid ReLU. That means at the negative size, we may also output a negative value. Okay, and the parameter may be changed depending on some characteristic. Okay, like alpha. Alpha can also be learned by the gradient descent, so we can adaptively adjust the parameter alpha to construct the activation function ReLU. So this is called parametric ReLU. You may wonder whether the activation function can be learned automatically. The answer is yes. In the recent research, there is a method called Mixout. Okay, Mixout is actually a special types of neural network. Okay, and we can use Mixout to learn the activation function. And ReLU is actually a special case of Mixout. Okay, the idea of Mixout is quite simple. Assume that we have two input, and then we do linear combination of these two input. And we may combine using different parameter. We may combine them to get the number 5, and with another combination we get number 7, and then we just take the maximum of these two values and output. So in this case, we will output the number 7, and so on. And this simple operation, actually the maximum operation, can be repeated many times, and we can consider more than 2 input values, and then we can consider multiple layers of maximum operation. Okay, so you can have more than 2 elements in a group, and this is the so-called Mixout network. And the activation function in the Mixout network can be any piecewise linear convex function, and how many pieces depending on how many elements in a group. So actually, the typical ReLU activation function is a 2-element Mixout network. So by appropriate design of the Mixout network, we can have the activation function like this, or maybe like this. And we can also consider maybe 3 elements in a group, so that the activation function can be separated into 3 pieces. And by adjusting the parameter, maybe we can generate an activation function like this one, or maybe generate like this one. And which one is better? That can be totally trained based on the training data. Okay, so we can use the Mixout network to learn the activation function. The fourth tip of increasing the training accuracy is called adaptive learning rate. So what is learning rate? Let's go back to the gradient descent algorithm. So initially we start from one point, and this point represents a set of parameters we use in the neural network. And according to the direction of the gradient, we will find a direction and move, or we say we update the parameter according to this direction, so that we will increase W1 and increase W2, so such that we can move from this point to this point. Okay, and by how far we move from toward this direction, okay, that is the so-called learning rate. Okay, so we should set the learning rate eta carefully, because in this case, when we move a lot, we may move too much, such that we may move to a place that is actually worse than the original, or we may move too much, such that the better update is not correctly defined. Okay, so if the learning rate is too large, then total loss may be decreased after each update. Okay, total loss may be decreased, may not decrease. Sorry, total loss may not decrease after each update. Okay, because we may move too much, although we move toward the correct direction, but we move too much. So the original loss may be 13.5, but if we move like this, the loss function would be 15. Okay, so the total loss may not decrease after each update. How about we just set the learning rate very small? If the learning rate is too small, that means we move toward this direction, but with very small scale. Okay, then the training would be too slow, because for every update we just move a little, and the optimal solution may be here, and then we need to move a lot of time to the optimal solution. Okay, so the learning rate, too large learning rate and a too small learning rate are both bad. Okay, are both bad. So how can we smartly do that? Okay, a popular and a simple idea is to reduce the learning rate by some factor every few epochs. Okay, so at the beginning we are far from the destination, so we can move much, and after several epochs we are close to the destination, so we reduce the learning rate. Therefore, we propose an adaptive learning rate eta that is depending on the numbers of epochs we have already conduct. So this is one possible parameter setting. Okay, that is called 1 over t decay. So every time the eta, the t's epoch, learning rate of the t's epoch is the previous learning rate divided by square t minus t plus 1. Okay, so this is one popular and a simple way to adjust the learning rate. And we know that learning rate cannot be one size fits all. Okay, so given different parameter and a different learning rate should be used. And there are actually more elegant adaptive learning rate method. One way is called etagram. So this is the original form to update the parameter. So from the original parameter, we may move toward the gradient. Okay, the negative of the gradient, and move the scale with eta. The other grade means we move with the scale eta w, where eta w is a parameter-dependent learning rate. Okay, that can be designed like this. So we divided the constant eta divided by this value, and this value gi is the gradient obtained at the ith update. Okay, and the summation of the square of the previous derivative become the denominator to adjust the learning rate. So this is one method that is called eta grant. And this is an example showing the effect of eta grant. So assume that right now we have two parameters, W1 and W2. And originally, with the original W1, we have the gradient 0.1. And with the gradient partial derivative to W2, the gradient is 20. Okay, so at the first update, we have the learning rate eta divided by the square root of 0.1 square. So we can see at the first update, the learning rate is this value. And at the second update, assume that after update, we have updated the W1 from 0.1 to 0.2. And then at the second update, we adjust the learning rate like this. Okay, and for the same case, we update W2 with the learning rate eta divided by 20 and eta divided by 22 at the second state. And from the effect of this example, we can see two observations. The first one is the learning rate is smaller and smaller for all parameters. So as the numbers of epoch or numbers of update increase, the learning rate keeps smaller and smaller, becomes smaller and smaller. Okay, no matter for W1 or W2. Okay, the second observation is that smaller derivative, larger learning rate, and vice versa. Okay, so here we can see that with respect to W1, the derivative is smaller. With respect to W2, the derivative is larger. And by comparing these two values, we see that the eta divided by 0.1 is much larger than the eta divided by 20. So that means smaller derivative will induce larger learning rate. Okay, and vice versa. But why? Why this design? We can see the visualization from this figure. With respect to W1, the derivative is small because if you go through from the left to the right, you will see that the loss, okay, the loss will not change significantly. Okay, but if you go from the bottom to the top, you will see the loss value change significantly. It will be 90.5 at the beginning, and then suddenly decrease to 10, and then decrease to 3, and then decrease to 1.5, and then increase. So with respect to W2, we have larger derivative. Okay, and according to the observation, according to the design of eta grant, we see that with smaller derivative, we will induce larger learning rate. With larger derivative, we will induce smaller learning rate. Okay, from this figure, you can imagine why. Because if the loss value changes a lot, changes significantly, we should be able to, we should keep our pace small so that we will not move too much and across a big range. Okay, across the big range. However, for smaller derivative, because from this direction, we don't have loss value change significantly, so we can feel safe to move more. Okay, so this is the idea of eta grant. And actually, in addition to adagram, we have many other adaptive learning rate method like IMSPROP, ADA delta, ADA second, ADAM, and NADAM, and so on. So there are many methods proposed to do adaptive learning rate. And if you use some toolkit, you may be able to easily change the learning rate by different method. So the fifth tip to increase the training accuracy is momentum. So what is momentum? Okay, usually it's hard to find the optimal network parameter. We are usually stuck at a local minima. Okay, so this is the main problem. Okay, so assume that this curve is the loss surface, and then initially we start from this. Okay, this point corresponds to some parameter, and then we need to update the parameter such that the total loss can be minimized. Okay, so according to the gradient descent, we may move from the left to the right, and then we update the parameter from here to here. And then again, we found the gradient is the negative of the gradient direction is toward the right. So we update this point to this point, and then we update this point to this point, and then we stuck at local minima. Okay, or sometimes we may, if we don't consider if the gradient value is just equal to 0, we may also stuck at a saddle point. Okay, so how can we solve that? Okay, actually the global minima may be here, but we may stop at the local minima. So in physical world, there is momentum. That is, if you throw a ball, you start a ball from here, and this ball will move from here to here to here to here, and because of momentum, there is a chance this ball will move to a not so high hill, and then go over this hill, and such that we have chance to go out of the local minima. Okay, so how about put this phenomenon in gradient descent? How can we implement that? So mathematically, how do we implement the momentum? Assume we initialize the parameter at this position, and according to the gradient, the orientation of the direction of the gradient, we decide to update this parameter toward the right. Okay, so right here we use the red arrow to show the negative of gradient direction, and we use blue arrow to show the real movement. So initially we will move this point toward the right. Okay, and when we move to this position, we check the gradient, and then we see here the magnitude of the gradient is smaller than previous one. And at this position, we also consider the momentum, because right here we move from the left to the right, and there it accumulates some degree of momentum. Okay, so actually, although the gradient, the strength of the gradient is small, but by adding the momentum, we actually move like this. Okay, and then we move to here, and at this point, the strength of the gradient is equal to 0. Okay, so in conventional gradient descent algorithm, we will stop here. But here, because we still have momentum value, so we also try to move this point to the right, and then we have the probability to move toward the higher loss. Okay, and at this point, the gradient, the direction of the gradient, negative direction of the gradient, is toward the left, and but the momentum value is still toward the right. So by adding the negative gradient and the momentum, we still decide to move this data point to the right. And after we go across the peak of this hill, then we have a chance to find a solution better than this local minimum. Okay, so by implementing the momentum idea, we have chance to find a better solution. However, we still don't guarantee reaching the global minima, but give some hope. Okay, so this is another tip to increase, or another tip to avoid a stuck at local minima. And if you use some toolkit, there is a learning method called ADAM. So the ADAM is actually the RMSPROP, the one of the adaptive learning rate method plus momentum. Okay, so you can use the optimizer, use the ADAM optimizer to find the best solution if you use Keras, the toolkit of deep learning. So from the toy example, as the numbers of epoch increase, and if we use the ADAM optimizer, then we can more quickly get the converged result. Okay, if we use the original optimization method, we may also achieve the same, almost the same result. However, using the ADAM method can help us to more quickly converge to a good result. Okay, and this is important when the numbers of training data is quite large. Okay, when we have many training data, then we may not be able to do many epoch. Then in this situation, using ADAM optimizer will be better than the conventional gradient descent algorithm. So now we have finished introducing 5 different tips to increase training accuracy. And as we said before, if you train your model very well, then your training accuracy may be high. Okay. However, even if you have good model to achieve high training accuracy, it does not necessarily mean that you will achieve high testing accuracy. Okay, and such situation is called overfitting. Okay, and to avoid overfitting, there are also several tips, and we will introduce these tips in the following. About the situation, the problem of overfitting. Why there is the overfitting problem? Okay, the main reason of overfitting is that the training data and the testing data may be different, especially the statistic characteristic of training data and testing data may be different. Like here, we see 2 sample images of the digit 2, and we see that the training data will be like this, but the testing data may be like this. There is an article, a circle at the bottom of the digit 2. So if we just train the digit 2 model based on such kinds of training data, we may not be able to very accurately detect or recognize such testing data, because the learning target is defined by the training data. So we define the best, we solve the best solution from the characteristic like this. However, the testing data may be like this. Okay, and the parameter achieving the learning target do not necessarily have good result on the testing data. So this is why we have overfitting problem. So we can simulate a toy example. For experiment, we can add some noise to the testing data. And then we do the evaluation. From the toy example, when we use only the clean testing data, we may have very high accuracy. However, for noisy testing data, we may have much lower recognition accuracy. So the training model, the model based on the training data, is not good enough to handle the noisy testing data. So one simple way to overcome overfitting may be add more training data, like some literature, some work has been proposed to maybe create more training data. Like if the original training data is like this, we artificially create more training data, like shifting, shift or rotate by 15 degrees, or do some shifting, or maybe do some flipping to add more training data. And according to the literature, such simple method sometimes really improve the recognition accuracy. So at the first, you can try this. You can artificially add more training data. But in the following, we will introduce several other methods from the perspective of machine learning to improve or to reduce the overfitting problem. The first method is called early stopping. Remember that when we train a model, we would expect when we apply the gradient descent algorithm, when the numbers of epochs increase, the total loss value would be decreased like this. Okay, this is the perfect situation. However, when there is overfitting, the curve of the loss function may be like this. That means when we train based on the training data, when we train for some iteration, some numbers of iteration, the best total loss can be achieved. However, when we increase the numbers of epoch, the total loss may increase. Okay, so in such way, we would like to stop at here. Okay, if we have some way to know that we have to stop here, then we can get the minimum total loss. Okay, so one way to implement the early stopping is that we don't really use the testing set. Okay, as we say, we may divide the testing set into two parts. One is a really testing set, and another is the validation set. Okay, you can imagine that this is a way to pick or to discover the characteristic of the testing set. Okay, so when we train a model, we may use a training set, and then we use validation set to tune the parameters. And after tuning, we get the final model. And given the testing set, we may have higher testing accuracy when we train model like this. And if we use some deep learning toolkit like Keras, this is a built-in functionality we can use to do early stopping. So this is a easy approach to slightly reduce overfitting. The second method is called weight decay. The approach of weight decay is motivated by our brain. Our brain prints out the useless link between neurons. So this is sample images from our human brain. At birth, originally we have few neurons, and when we grow up, starting from the birth to the 6 years old children. The 6 years old children, the neuron would be quite complex, and many neurons are linked. However, when the children grows from 6 years to 14 years, actually some useless link will be pruned. Okay, so we can see the links between neurons are simplified. Okay, so doing the same thing to human machine brain improve the performance. Corresponding to image recognition, let us take the digit recognition again for the example. For recognizing this digit, we can see that actually the border of the digit corresponding to the image recognition task. How can we implement the weight decay and the idea of weight decay? Imagine that from this digit image, we can see that at the border are usually in white. So basically, there is often no information at the border of the image. Okay, and the border, for example, would corresponding to maybe the last few neurons, and the links or the weight related to the last neuron would be useless. Okay, so we want to mimic our human brain, the characteristic of our human brain. We want to reduce the useless link, the weight of the useless links to be smaller and smaller if these neurons are really useless. Okay, so how can we mimic that? Okay, and basically the weight decay approach is one kind of regulation if you understand the mathematical formulation. So how can we implement that? So originally when we use the gradient descent algorithm, we update the parameter w by this. Okay, so we update w as the w minus this is the learning rate and this is the gradient. And the weight decay is simply we apply a parameter that may be like 0.99. Okay, and we multiply 0.99 to the original w and then do the gradient descent. And if this weight is useless, if the corresponding link is useless, we will keep multiplying this value again and again, and then the update parameter will be getting smaller and smaller. So this is how we implement the weight decay approach. In deep learning. Okay, and if you use some toolkit like Keras, we can easily set the weight decay. We can easily implement the weight decay. The third method is called dropout. Dropout is a very weird or very novel idea to reduce overfitting. The idea is this: at each time before updating the parameter, we drop out or we discard p% of the neuron. Okay, we randomly discard or ignore the information of p% of the total neuron. So at this epoch, we may ignore this neuron, this neuron, this neuron, this neuron, or this neuron, this neuron. That means all links related to this neuron are set to be 0. Okay, and at the next time for updating, we may randomly select other neuron to be ignored. Okay, so this is the simple idea of dropout. So when we discard some neuron, actually the whole network become thinner. So when we discard some of them, the structure of the network is changed. Okay, and we use the new network new network for training. Okay, and for each mini batch, we may resample the dropout neuron. So at each time, we discover different neurons. And at the testing, we don't do dropout. So at testing, we use the whole network to do testing. Okay, so and remember that if the dropout rate at training is p%, then all weight will times 1 minus p% to normalize the learned weight. Okay, so assume the dropout rate is 50%. Then if a weight W is equal to 1 by training, then we set W is equal to 0.5 for testing. So this is for normalizing the difference between training and the testing. So why such simple idea can reduce overfitting? The intuitive reason is in the following. When teams up, if everyone expects the partner will do the work, then nothing will be done finally. Okay, so when you form a team, like there are 4 members in a team, when you think about, okay, my partner will do the work, then I will be too lazy to do the work. However, if you know your partner will drop out, you will do better. Okay, so if you team up, and if you know that your team member will not work at all, then you may work harder to handle your problem. Okay, so if everybody think about to do harder to make the job done, then if you all the team member think so, then the power of the whole team will be improved. So this is an intuitive reason. So when testing, no one drop out actually. So obtaining good result eventually. Okay, so this is a very intuitive reason, and to make such simple idea workable. And why the weight should multiply 1 minus p%? Okay, what is p% is the dropout rate when testing. We have some mathematical reason. Okay, so in training, assume the dropout rate is 50%. So every time half of the neuron will be discarded. Okay, and when testing, we don't do dropout. So we need to multiply 1 minus p% to do so. Okay, and actually there are some mathematical derivation to prove that this weight adjustment is important. There is another viewpoint to explain why dropout work. Actually, dropout can be viewed as a kind of ensemble. Okay, so the so-called ensemble is a collection of models. You can see that. Okay, so given the training data, we can divide the training data into several sets. So based on the first set, we can train the network number 1. We can, based on the second set, we can train the network number 2, and so on. So we can train a bunch of network with different structures. So this is a so-called ensemble, a collection of network. And when given a training data, we can input this training data to 4 different networks to get 4 different results. And then we may take average or maybe other fusion method to recognize the testing data. And when we apply dropout, actually when we design a framework, we at different mini batch, we randomly discard part of neuron. So for the first mini batch, we may discard this neuron, may discard this neuron, and this neuron. So we can think that the first mini batch is part of the training data, and then we construct a first network to do the classification or recognition. And based on the second mini batch, it can be viewed as the second training data set. And then we discard this neuron and construct a different network. So this is network number 2, and so on. So we can view the dropout as construct several thinner network based on different training data. Okay, so we can get many possible network, and we can view them as an ensemble of networks. Okay, so we use one mini batch to train one network, and some parameters in the network are shared. So different networks are necessarily totally different. Some of them share the same neurons and the same parameters. So when testing, we give the testing data and input this testing data to different network, and we can get several results, and then we average the final result. And basically, we hope the average result of the average of the result of several thinner network may be better than the result obtained by the whole network. So the previous slide showed the idea. We can view that dropout is an ensemble approach, and actually there are also many other variants on using dropout to reduce the overfitting problem. Like dropout works better than Mixout, like drop connect. Okay, dropout delete neuron, but drop connect delete the connection between neuron. Or there are also some work called linear dropout. So the dropout rate will decrease by epoch or stand out. Each neuron has different dropout rate. Okay, so there are many variants proposed recently. So we can also try based on our toy example. So if we use Keras, we can simply add a dropout layer such that we can randomly drop out some neuron, like 80%. Okay, and we can easily do so. And this sample result shows that when the numbers of epoch increase, when we apply dropout and no dropout. Okay, so basically, if you apply dropout, the training accuracy will be decreased. Okay, if we don't use dropout, the training accuracy will be higher. However, this is for training accuracy. However, for testing accuracy, if we don't use dropout, the testing accuracy may be 50%. If we use dropout, the testing accuracy may be increased to 60%. Okay, so usually when we apply dropout, the training accuracy decrease. However, the testing accuracy increase. And when we do real application, we need to make a trade-off between training accuracy and testing accuracy. And basically, we may put more focus on testing accuracy. So dropout is a way to find a trade-off. The final recipe to reduce overfitting is the network structure. Okay, we may need to design different network structure to reduce overfitting. And right now, we just mentioned the fully connected neural network. But actually, for many image analysis work, another neural network structure may be better, like convolutional neural network. Okay, so CNN is a very good example that can be used to reduce overfitting, and we will describe CNN later. So in conclusion, when we try to do deep learning, we first have to define a network structure that is corresponding to defining a set of functions. And then we need to define what is goodness of a function. And then we can use the gradient descent algorithm to pick the best function. And when we train a network, we first need to evaluate whether we have already get good result on training data. If no, we have several tips to increase training accuracy. If we already achieve good training accuracy, then let's check whether we have good testing accuracy. If no, that means our model is faced with the overfitting problem. Then we have several tips to reduce overfitting. Okay, and then if we apply this technology to reduce overfitting, we may have better testing accuracy. And if we apply all the tips to do this work, but we don't have high enough testing accuracy, that means we may need to redesign the whole framework, or think about if there is other information we can use. Till now, we always use the digit image recognition as the example, but actually deep learning can be widely applied to many different applications. So let's try another task. We can do document classification. We can represent a document by a vector. For example, the first dimension may represent the appearance of the stock, the word stock, and the last dimension may represent the word precedent appearing in a document. So we can transform each document into a vector, and then we can construct a network to classify a given document into one of the types. Okay, that may be a political document, economic document, or sports document. So we may have a toy data, and then if we measure the loss, if we measure the total loss, okay, by different way, by maybe mean square error or cross entropy, and when the numbers of epoch increase, the training accuracy may also increase to some extent. So in this case, using cross entropy is better. And then when we try to change our activation function from sigmoid function to ReLU, then we can see that the training accuracy boosts a lot. Okay, when the numbers of epoch increase, the training accuracy boosts a lot. Okay, so this example, by comparing this slide and the previous slide, we can feel the influence of activation function is actually larger than the influence of loss function. And then if we try to use the adaptive learning rate like we use Atom, then we can have higher training accuracy when the numbers of epoch is small. Okay, and if we keep increase the numbers of epoch, then we may have similar training accuracy. Okay, and here we see that the best accuracy based on MSE, cross entropy, and plus ReLU plus Atom is the training accuracy. If we use the ReLU plus Atom, we have the best training accuracy. And for dropout, if we train without dropout, we have higher training accuracy. And if we train with dropout, we have slightly lower training accuracy. However, the testing accuracy may be higher. Okay, so we can see here we show the testing accuracy. The testing accuracy may be higher.